All right, so this is the start of a video lecture series on chaosbook.org. We're going to cover classical and quantum chaos theory and dynamics. This is meant kind of as a study along for me. I'm trying to learn quantum field theory, and I have background in dynamics and neuroscience, and so this is kind of trying to develop my theoretical understanding of how dynamics can be used in physics. So I'm going to be posting probably a video a week on at least one chapter of the book each time, and hopefully we can get through the whole thing. Prerequisites so far are these 3 books, essentially. You should know some mechanical physics, right? You should understand the Lagrangian, Hamiltonian formalisms, how particles move, how to calculate energy, basic systems like harmonic oscillators. So this middle book is a great introduction to all of this. Highly recommend it. If you need help, we have a server, a Discord server, where you can come and ask questions. This is sheafification.com, and there's a little link to our Discord server on there. But I'll write that real quick. Let's see. Where's the insert text button here? So that's... at the top right, you should see a chat button where you can join a Discord server. You should read this book as well, Applications of Lie Groups to Differential Equations. It introduces the theory of manifolds, of Lie groups and Lie algebras, how to apply them to differential equations to calculate the symmetries of those differential equations, how to solve PDEs using symmetry methods, and a variety of other things that will be useful for this course, or for this lecture series. The book by Kuznetsov is an excellent introduction to dynamics and bifurcation theory. It can replace Stephen Strogat's nonlinear dynamics and chaos, which is a more common first introduction. It contains all the content in that book and a large amount more. Like it covers the theory of homoclinic chaos, a variety of things that are not well known to people outside of the professional dynamics community and the old Russian literature. So this is an excellent book. I recommend everybody read this. I will assume that you have knowledge of all 3 of these things in developing this lecture series. I had started doing a group call where I was introducing some of the stuff here, so this is not going to be strictly part of what I'm going to cover today. You should know essentially what I was covering there already from having read most of the Kuznetsov book. But today I'm just going to cover chapters 1, 2, and 3. So this is just on dynamical systems, both continuous and discrete dynamical systems. Part of this is going to be converting back and forth between continuous and discrete, as well as just some terminology to get started. So a dynamical system is a pair, M and F, right, where M is some kind of smooth manifold. And you should know what that is from Olver's book. So a curve is a 1-dimensional manifold, a surface is a 2-dimensional manifold, some kind of voluminous object is a 3-dimensional manifold, and so on. You have 4-dimensional, 5, so on. There's also infinite dimensional manifolds, but in general, we're going to be dealing with finite dimensional dynamics up until the second half of the book, of Chaos Book. And F is what's called an evolution map, right? So that's a function that takes a point in M. So that's a state, because M is your state space. It's where your dynamical system currently is. And F takes a point, a state, as well as a time in the real numbers, and spits out another point in state space, right? Another state. So it takes your current state, an amount of time to evolve your state for, and spits out the resultant state of the time evolution. And this function is smooth. Okay. That is the entirety of chapters 1 and 2 in this one slide. There is no more. There are some terminology divergences or some coverage of terminology like periodic orbits and so on, but it's not necessary. We'll talk about this when we actually use the subject. So all of the dynamical systems that we'll look at are Markov. They have the Markov property, which means if you know the current state, then you're able to figure out where you're going to be in the future without any additional information, with absolute certainty. It won't quite be true for the quantum systems we deal with, but at least for all the classical systems that we look at, this is going to be the case. So if you know where you are, the evolution operator will tell you without any additional information where you're going to be in the future. Additionally, most of the systems we deal with are going to be described by differential equations. And these differential equations are often going to be algebraic and so on, nice and smooth. So we won't have to worry about non-uniqueness, non-existence of solutions, at least locally in the parts of state spaces that we're going to be caring about. So you do have uniqueness and existence. So those, the relevant properties of solutions to differential equations in our dynamical systems, the trajectories, are going to apply in general. One key characteristic of the dynamical systems that we look at is that they're chaotic, which means if you look at an initial point, say, I kind of drew on the slide already, but let's say you take a particular location in state space. Just kind of ignore this red stuff for now. This is called the Poincare surface of section, but don't worry about that. So let's say I take an initial point in state space, say right here, and I evolve it in time. So I'm going to get some kind of trajectory that follows a path like this, right? It's going to be on this yellow string. And it's going to go around, and I'm just going to kind of sketch sort of what the behavior might be in some sense. And it might go around, and it might come around this thing, and then flow back out, and then jump over here. And you don't know how many times it's going to go around each leaf of this is what's called a Lorenz attractor ahead of time, right? You can calculate it for one or two traversals of each leaf, each side, but you're not going to be able to predict well in advance what the sequence of left, right is going to be. Like left, 7 times maybe, and then right twice, and then left 3 times, and then right once, and then left 5, who knows? And also, if I were to look at a trajectory just beside this one, arbitrarily close, 1,000 zeros, 0.1 difference. Not 0.1, but 1,000 zeros and then 1. After a pretty small amount of time comparatively, the two trajectories are going to diverge from each other in behavior, so you'll end up having different symbolic sequences of revolutions around each leaf of the Lorenz attractor pretty quickly, no matter how close together the 2 points are. And so normally in dynamics, we'd like to be able to say, okay, where I am determines where I'm going to be and what I'm going to do. But if I can't look at where I am with any amount of error at all and determine what I'm going to end up doing qualitatively, then we say that the system is chaotic. I can't predict what's going to happen based on where I am with any, lack of precision at all. I have to have exact solutions, otherwise I don't know what's going to happen long term. So the point of a Poincare return map is you want to quotient out the time translation invariance symmetry of systems to differential equations which are autonomous. Now this does not work if they're not autonomous because the systems won't have that symmetry anymore. The idea is you pick out a section in your state space, like the red one I've drawn here. This is called the Poincare surface of section, or a hypersurface of section, because if we're working in 2D, I might draw a picture of what that looks like. If we're working in 2D, if I could select my marker, that will, we might have trajectories that look something like the following. So that's one, and it's periodic, right? So it goes around over and over and over, and then you might have another that looks something like this. And it kind of goes around over and over and over, but never intersects with the others, even though I kind of drew it doing so. And you need to sort of draw a surface, a hypersurface, that cuts through all the trajectories transversely and captures sort of all of them locally. Well, all you need is a curve, right? So this will capture this point on that curve. It'll capture this point on that curve, this one, that one. And they'll all go transversely. I don't want it to be tangential, so I wouldn't draw it in some way that looks like this, because that would end up giving me a kind of poor-looking return map. The idea is I come up with a coordinate system for this map, and this one is pretty nice, actually, because the way it would look is I have a coordinate system, which might be like 0 right here, and then this might be 1, which, would be there. This is 0, this is 1, and I might draw what my points that have hit the return map have done. So I ask, okay, well, when am I on the map? Well, I'm on the map right here. So I can go over here to the return map and look at this point, which looks like it's roughly like at 0.8 or something. And it looks like when I follow the trajectory, it's going to go around, and then it'll come back, say, right here, maybe at like 0.6 or something. And so that maps to here. And then I have this one mapping to right here, so like 0.4, and then maybe 0.3. Or, maybe it doesn't. Maybe it goes to 0.35 or something. And then it asymptotically approaches this point or something like that. This one, because it's on a periodic orbit, will map back to itself, certainly. And so the way I draw this is I can draw a bisectrix that's a 45-degree line, like so. Oops. Let me fix that a bit. And our dynamics will be described by a function. What color should I use? Let's say red. Let's do black. And that function will have a fixed point right here, where that periodic orbit goes through. And above, let's see, it's going to be stable, so it probably looks something like, maybe maybe something like this. So really I should be more careful. I should say, okay, well, this point will have mapped up to here. Or rather, how should I draw it? It should have this point as an image. And so I want to say maybe it should be at this height. And this one wants this one as an image, so it should be somewhere around this height. And then this one wants this point as an image there. And then it kind of just approaches like this. So this might be what the map looks like. And the way you evaluate this thing is you say, okay, well, I start here, and I want to evaluate the return map. I want to iterate it. And so I go up to where the function is. And there's a unique point because it's a function, so as is the vertical line test, you go over horizontally to the bisectrix. You then go vertically to the curve again, the function. Then you go back to the bisectrix horizontally. There's a unique point where that is met. And then you just follow like this. This is called either a Lamoury diagram or a cobweb diagram. Most people call it a cobweb. Oops, I'm not able to draw now. Well, I think it froze. Okay. All right, so this will asymptotically approach that fixed point. Now, we've reduced the dynamics down to this return map, and I can have gotten this graph by evaluating all the points in between. All right, so I would have had to have taken this point as a sample and watched its trajectory as it goes around until it comes back. So, it'll go around, and likely it won't be here, it'll be in here. And it will have mapped into here. So something like this point. Okay. In 2 dimensions, you have 2-dimensional maps, and they're just maps from U to U. And they're smooth still because they inherit smoothness from the full system, unless you take your section in some strange way. Sometimes it's useful to do so. But yeah, you might have a map that looks like, okay, here's a point. You let it evolve in time, and then you capture when it comes back to the surface of section, and it happens to hit right here. So you'd have this point mapping to that point. And then this point might map down to this point or something. Who knows? But every point maps to some other point. And you have injectivity because your surface of section is taken transversely to the flow. Okay, so the book talks about Poincare sections and Poincare return maps. And it introduces some terminology, such as template points. And so a template point would be, okay, let's say I want to construct a return map in the system. Well, let's delete all this. I don't have my return map yet. Okay. So I need to take some kind of Poincare surface of section. And I might look at a point that I'm interested in. So I want to know about the behavior in a neighborhood of this point here. Okay. So I call this a template point. This is x hat. I look at the flow here. So say like this. Tangentially, this is a tangent vector to the flow. So this would be the velocity. Okay. And I treat this as a normal vector to the surface of section. And then what I can do is I can construct some kind of linear hypersurface. So in this case, it's actually a surface. So you construct a hyperplane normal to this normal vector. And so in our case, that would look something like this. And you can extend it out in some such a way that you don't end up having trajectories tangent to it at any point. So this is locally defined because I can always take a small neighborhood of the point and construct a hyperplane because of smoothness and continuity conditions. Namely, if the normal vector here is pointing this way, then it can't be that for any small neighborhood around this point, there exists a normal vector, which is, or, some kind of flow vector, which is pointing orthogonally to it. Continuity dictates that the flow vector has to change at some continuous rate, right? So there should be some neighborhood of the point that I've taken, the template point, x hat, in which the flow is approximately equal to n hat. Right, so for us, x hat is the template point. And n hat is the tangent flow vector at x hat. And yeah, n hat lives in the tangent space to m at x hat. So you just extend out in a neighborhood normally to the normal vector, or orthogonally to the normal vector. You extend out a hyperplane, and this will give you a Poincare surface of section locally always. It's not the case that every point in it will map back into the into the plane, but at least you can take, let's say this is an unstable trajectory and everything nearby it kind of diverges from it. It's repelling everything nearby, gets pushed away from it. Then what you might do is you might say, okay, well, how can I get a Poincare surface of section locally to this thing? Well, let's say, your flow goes out in this way, so that's n hat, and this is x hat. And, locally, all of the points out normally to here and to here in a circle, maybe they're all transverse. The flow is transverse to the hyperplane in all these points in this circle on the hyperplane. Now, it might be the case that, you sample this point and let it evolve in time, and it comes back and goes out to here on the hyperplane. Well, you can just say, well, I know that this point comes right back. Let's say it comes back and hits right here. Well, I know I can take a neighborhood of these 2 points by continuity, where everything in this neighborhood on the hyperplane maps into the blue part. And so there's always some way to get some kind of local Poincare surface of section that actually works and captures everything. But it's not the case that you can iterate it arbitrarily many times and it will still remain closed, right? You might get trajectories that go out of the Poincare surface of section, in which case you just wouldn't draw them, right? Wouldn't draw their images on the flattened version that you're drawing on a diagram by itself. But at least locally, you're guaranteed to have a well-defined map on this, and it's locally guaranteed to be closed. Not in the conventional sense where if you map one section through the return function, it will be strictly where it was or in a smaller set, but you're guaranteed to be able to trap everything one iterate ahead, so you're fine. You can at least study the dynamics using this always for smooth systems. Just to comment, another thing that's commonly done when you have high-dimensional maps like this, like you might have a 2-dimensional or 3-dimensional or higher map, is you pick out some kind of one-dimensional projection, and that way you can then draw a cobweb diagram. So you might say, okay, well, I've got a return map in 3D, so I necessarily have a 2D surface of section. How can I turn that into something I can do a cobweb diagram with? Well, in this case, it kind of makes sense to say, okay, well, this dimension here, I should just project everything onto it. So I might say, okay, well, if I have a point here, let's draw this in the flattened 2D version. It keeps taking me there. Okay. So that might look like a line like this. So this point here, I would just project that down to here. And then I would have a map from this to here. And then I get a map on the 1D subspace, right? It turns out that this won't be a function necessarily because you might have had a point here in the 2D map and a point here in the 2D map, and this one might map to here, and this one might map to here. So, this goes like that, that goes like that. And the way this would look in the projection would be that this point goes both to here and to here. And then the cobweb diagram, you would fail the vertical line test. But in a nice contractive system where everything's kind of flattened, I might pick a point up here for my trajectory, but it'll quickly just kind of converge onto the ear here. When you have strong contractive forces like this, you don't really care because it's going to look mostly like a function with some small noise, right? The cobweb diagram that you get out will have a function that looks very function-like, and it's not going to have strong, non-well-definedness. We might have tried to construct a Poincare surface of section that's normal to every trajectory that passes through it. And this can be done in these smooth systems, so long as you don't pass through a fixed point. That's not really a problem, but it doesn't help you much. Like if you're on a computer and you're trying to simulate a dynamical system and you're using like an Euler or Runge-Kutta 4 solver, and you're trying to discretize it by forming a Poincare surface of section and computing the return map, you don't really care about having trajectories flowing normally to your surface of section. It doesn't matter that much. Having transverse flow to the surface of section is pretty much as good as having normal flow. And so it's fine to just take these linear subspaces. You don't need to care about, in this case, if I were to take a normal section, I might start with a template point like this. And then I say, well, okay, it has a tangent vector that looks like this. And so maybe I need to look this way to start with. Well, to stay normal, I have to deform a little bit when I'm forming my surface of section. So a 1D subspace of the surface of section would flow in some fashion like this, and it would always be normal to the flows that go through it. And then these might continue on upwards. Who knows? Who knows what they'll look like? But it won't be a line. And my full surface of section might be this kind of deformed thing if I form it in this way. On a computer, this is quite hard. There's not a good algorithm for doing this quickly, and it's not important to do this either. So don't worry about doing that on a computer. Just form a linear, hyperplane surface of section, and you'll be good. If you care how fixed points and invariant sets in your state space organize the dynamics of the state space, you should allow your surface of section to pass through those fixed points and invariant sets. So in this case, I might take a surface of section that looks something like this sort of thing. We've already looked at doing this kind of with the blue one, but I might extend it out and let it just pass through or go up to the fixed point here. So this is a fixed point of the system, and I might let it go through that. I probably wouldn't make it go all the way through and come out to the other end, simply because that kind of introduces some redundancies. Like if I let it go over here, then this trajectory is going to go around and it's going to hit this other one, and it's not really a return. You could take the second iterate of such a return map and it would give you what it would look like to come back around and hit on this side most likely, most of the time, but it's still going to kind of be degenerate in a way. It's better to just look at only the right-hand side. Yes. Also, when you are taking slices through equilibrium, you should prefer being tangent to stable manifolds. Okay. So let's say there's a common system called the Shelnikov attractor, and it looks like this. So you have a fixed point, and you have a stable direction, so a stable manifold, and you're in 3D, and you have an unstable manifold, which is a spiral. So you flow out in a spiral asymptotically. And you have countably infinitely many revolutions as you go back in time towards the fixed point, and you're flowing outward. And then you come up, and you go up to here and connect. So this is a homoclinic trajectory. If you were forming a return map in a naive way, now for this system there's a kind of canonical return map you should use called the Shelnikov map. But if you were just forming a Poincare surface of section, you would want it to be tangent to the stable direction to this fixed point here. So, you'd want to make it be like this and slice through this stuff. Right. So this would be the slice. This point would be on that trajectory, would be on the surface of section. This would too, this would too, this would too. So that would be, you wouldn't want to take it in this way. Like flat, where the spiral's on it. Now, if you just flip the direction, so you reverse time for this system, then yes, it is going to look like this, because now this is going to be the unstable manifold, and this will be the stable manifold. And of course it's homoclinic, so really they're both the stable and unstable manifold. But if you're looking at the non-homoclinic case where this just spirals out, and this comes from infinity, then, because this is a spiral, it's kind of a bad example for this, but if it weren't a spiral, you would be okay doing this. Okay. So if you have a two-dimensional stable manifold, then it's most likely not going to be the case that this is going to be helpful. But if you have a two-dimensional stable manifold in a three-dimensional system, then it's going to be a strongly attracting fixed point most of the time. And you're probably not going to be looking at Poincare maps anyway, because you probably won't have chaotic dynamics. Most of the time when you have chaotic dynamics, you have a lot more unstable manifolds than you have stable manifolds. Things are repelling more than they're attracting, and so you don't get stuck in basins of attraction as much. And so you don't have this problem really most of the time. But yeah, prefer the stable manifold to be tangent along most of the time. All right, so sometimes it's quite hard to actually get the full structure of a return map. In particular, on the left side here, sometimes, so what you usually do is you pick out a Poincare surface of section, you establish a coordinate system for it, and then you sample uniformly most of the time along the slice that you're interested in. So you'll take not only a Poincare surface of section, but oftentimes you'll just take a single slice, a one-dimensional line through the state space, and sample uniformly on some interval along that line. And you'll get a point here, 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 all evenly spaced, and you'll see what heights they produce on the graph. Now, this diagram is showing, from a paper my advisor wrote, a bunch of different return maps. So one of them is, say, this. So he ran some trajectories sampling the map and got this. Not sampling the map, but sampling this the flow in the full dynamical system, and then discretized by taking the Poincare return and got this thing. Okay. And then he changes the parameters for the dynamical system, and then he'll get some other kind of curve, like, he changes the parameters a little bit, and he might get this one, right? The one that is nearby. Oops, it goes down like so. And then, you can reach all of these different curves, these graphs, by changing the parameters in some way. Now, the problem is at the steep parts of the graph, you're not going to be able to get many samples. And this matters quite a lot because the behavior is changing very drastically in that region. And so you want to understand how it's changing. So if you sample uniformly, you're going to get a point here, and then you might get one here, and you don't understand what happened in between. So you might try bisecting, right? You might try taking, if you took right here, you might try taking dead center. And then you see it goes right here. Well, it's really close to this one, so that doing some kind of linear interpolation probably isn't a bad idea on this part. But here it seems like a quite bad idea because you don't know if it's linear. There might be some interesting curvature to the map. So you bisect yet again, and you end up getting something like this. And then you're okay, linearly interpolating here. Maybe you still want to sample more, but this still seems really bad. You don't want to linearly interpolate that. So you continue bisecting everything that jumps too much from point to point. And this does work. But the problem is it requires you to iteratively bisect until you get everything. And the dynamics are really, how do I say this? Expansive in the full system in places where this is happening. So you might be near a saddle fixed point or something like that. And so you're going to be highly susceptible to numerical inaccuracy. So you might not even be getting real trajectories because you might have floating point imprecision problems going on that are getting exacerbated by the dynamics. You might have a stiff stiff system of differential equations or something like that. And the solver that you're using might not be good. Your tolerances might not be big enough, so on. So how do you ensure that you get a good map? Well, there's a few methods. First, you can do bisection. You can tune your tolerances until you're getting something consistent. What else? You can use optimizers. So for peaks like this, the red one, you can use an optimizer to find the highest point because, you would be bisecting here, and you'd find that, and then you would bisect between them and you'd get something like right here. Bisect again, you might get something like this, and you continue going up, but you don't ever really know if you're high at the peak, right? You don't even know if there is a peak. There might be some kind of critical point where you're flat, but in a really small neighborhood, so you don't know. So you can use an optimizer, which will recursively search within smaller and smaller intervals and find this for you, hopefully. So different languages provide different packages. In Julia, I like to use optim.jl. There are various packages for Python and so on, MATLAB. But for Julia, this is what Collab usually uses. But there's also another trick that I learned from my advisor's paper, which, this excerpt here explains it. So if you have a dynamical system and you introduce some noise into the trajectory, just taking a Gaussian distribution, sampling it, and adding that to the state at every point in time along your integration, your Euler solver, you can induce chaos, right? So you might jump between different regimes by accident. So you might actually be in the basin of attraction of a fixed point, but you jump over a saddle invariant set and end up in the basin of attraction of a different fixed point by making a small perturbation up to like some Gaussian distribution. So that's quite bad. You don't want to do that. You don't want to disturb the dynamics in such a way. But if you have the issue of super finicky return maps and they're super steep, noise can elucidate, as you can see in this diagram a little bit. It can help you get the map uncovered in some sense. Now these are for different parameters, so these aren't the same map, so the fact that they look different is of no consequence. And I couldn't find the best map that I've seen showing this noise technique, but sometimes you'll see it actually uncovers the entirety of it, so there won't be a gap here. But this technique is really useful because it lets you take many less samples than you would need to if you were doing a uniform sampling. And you can just do some kind of regression or something like that. Or you can make a pretty good guess at what the true return map ought to look like just by adding some noise to your trajectory. Now, in certain cases, it makes more sense to do to introduce noise in a certain way. Like for this, there is a voltage for spikes, like a maximum voltage for a spike of a neuron in a Fitz-Unigomo neuron model. And we're using the max voltage the max voltage observed for the return map. Now, this isn't strictly using a Poincare surface dissection. It's just saying, okay, I reach a local maximum in voltage. I record that. I wait until I see a new local maximum in voltage above a certain threshold, and I record that, and I see what I started with now, which might be like, negative 38. And then next time, if I saw that, I might see something like negative 48, which is my height here. So that would be a point right here. No, that's not really a Poincare return map. It's just a iterated map of some sort, but it's an interval map of voltage. But the technique applies, and we don't just add noise to any point. We add noises to the inputs to the dynamical system, like, say, the synaptic voltage or current or something like that. So you can introduce it in different ways. It doesn't have to strictly just be a Gaussian distribution being sampled and added to where you are in state space. It could be perturbing some variable or parameter in some way. And this will often preserve the overall structure of the map and illuminate it a little bit for you. So it makes it more efficient to uncover the structure of the map. I should also note here that when you do have chaotic dynamics in the full system, the value of a Poincare return map is that oftentimes, and I would say almost always, if you are clever in your choice of Poincare surface of section, you will be able to take a chaotic system and get non-chaotic maps. Or if they are chaotic, then their geometry is well-defined and looks very much like a function graph. And you can study the geometry of the graph using methods from combinatorial dynamics, and you will learn a lot about the dynamics of the overall system and gain new tools for bifurcation study. Now, Chaos Book in Chapter 3 covers one last topic that I'd like to talk about, and this concerns how you actually form return maps. Now, let's say I have some kind of 3D system, or it doesn't matter, we can look at 2D. That's fine. So let's say our state space is I cross I, so basically a square. And let's say we have a fixed point here. And I take a surface of section, or hypersurface of section, which is just the ray coming out to the right from the fixed point. So if this is R2, that would be the positive part of the x-axis. Now, what happens when I construct the return map is I need to look at an interval on this surface of section and sample a bunch of points. Let's say I sample this point initially. Well, I go into my Euler solver, or my RK4 solver, or whatever, but let's just say it's Euler for simplicity, and I figure out what the derivative is. The derivative is giving me a tangent vector pointing in this direction with this magnitude. And so I have a certain step size, which is quite small, and maybe it's like 0.01, maybe it's 0.1, who knows. So I just divide the length of this vector by 10, and I go to that location. So I go here, that's my new location. Now maybe my new derivative is pointing in this direction, so I go a little bit in that direction. And let's say I continue to do so. So I have piecewise linear jumps, and I just flow around in the space like so. Now what will happen is my next point from here might be here, and then the next point I get by my Euler solver might be here, and then the next one may be here. Now it's clear to me that I have just passed over the surface of section. The question is, where did I pass over it? Now I could decrease my step size for my solver and make this easier to see. I might end up here, but then I still don't know where I passed over. I could have in fact passed over right here, because I might have a derivative pointing this way, but then it quickly changes and sends me flying over to here, and then I come back and go through like that. That's a possibility. So how do I actually know where, how do I stop integrating right at the surface of section? That's my question. So Chaos Book gives us a nice little computational trick that lets us do this. So the first step is you want to come up with some function on your state space. Let's call it U. So U is a function from your state space M to, so this for us is M, right? I cross I. And this function U should map from your state space to the real numbers, and in particular, on your Poincare surface of section. So if I restrict U, the Poincare surface of section, it should equal the 0 function. Okay, so it should be equal to 0 whenever I plug in a point that's on this Poincare surface of section. So I should make that one blue, really. All right. In particular, you want it not to be, you can have it be 0 elsewhere, that's fine. The problem is when specifying a function like this on a computer, it's a little easier to, just, for example, U might be equal to, you take X and Y coordinates, where this is 0, 0, and it might be equal to just Y, the height. Of course, it's 0 on the Poincare surface of section, right? But it's also 0 over here. Now, a nice differential equations library, like in Julia, will allow you to stop the integration when you are crossing 0 for U from below to above. So only when you're doing it this way, not when you're going this way. However, you might have some issues because your flow might be, let's see, your flow might go something like this in some locations. You might start here, it might go around, come back down, and then like this. this would throw some problems. So just assume that I have a function that, assume that my flows don't do that in our case. Assume they all just go positively along theta in polar coordinates. So they all go counterclockwise. They don't ever backtrack at all. Then we can say that u is y, and we only stop the trajectory and say that we're on the Poincare surface of section when we're passing 0 from below to above. Now, particularly in Julia, you can specify what's called a continuous callback, and it will search for the location that you actually pass the surface of section where u is 0. It will do some kind of bisection thing and solve for the exact time that occurs. However, if you use a discrete callback, or if you're writing your own software, you might want to use this optimization trick that I'm about to show. We might have a system of differential equations specified in this kind of way for our flow, which would be something like dx dt is a function of x and y, and of t if you want, but doesn't matter. And then you might have dy dt equals g of xy, and this is enough to specify the flow. Now, for the 2 points, this is going to be just purely theoretical. For the 2 points around the time in the integration that you're doing, the numerical integration that you're doing, where you are passing over u equals 0, which is the surface of section, we'd like to call this point at time t sub a. Whatever the time in your integration is, call that t sub a. And after you pass the surface of section, when u goes to positive, call that t sub b. Those are the times. What we'll do is we'll manipulate the system of differential equations governing the flow such that we convert one of the spatial coordinates into a time coordinate in some sense for the purpose of reintegration. And that will allow us to integrate up exactly along a quasi-time interval wherein we end up stopping exactly at y equals 0, or in particular u equals 0. So now note, let's go back to the system of differential equations. I can go down to y, and I think we'll probably end up converting time into y. So I want to manipulate dx dt, right? So note that f is equal to dx dt, which is by chain rule equal to dx dy, dy dt. And this is equal to dx dy times g xy. Now, time can be written as a new quasi-spatial variable, so t can be differentiated with respect to y. So in this case, that means, how should I do this? Yeah, so dt dy ends up being 1 over g of xy, and dx dy ends up being f of xy over g of xy. Let's highlight that, because that's our new system. You can, of course, put in the initial conditions here, which would be at time ta. You, I think, will have to re-specify your dynamical system, your system of differential equations, in the computer so that, you'll have to provide the new algebraic definition that you derived by hand, and then integrate that with y being the new time variable. But you can stop with y being exactly where you want it. And in particular, I believe you could probably do this with u, just changing u into your time variable so long as it's nice enough. Because you have the fact that you're pretty close to the surface of section already when you start, with ta being your initial time. You can probably locally do a change of variables that allows, a coordinate transformation that allows you to treat u as an integration variable. So that would work when u isn't just one of the coordinate axes already. Yep. So once you've gotten the dynamics rewritten in terms of y as your time, you should be able to just integrate that on the computer and run over a certain time span. And you then will have the exact location at which you are on the Poincare surface of section, and you can stop there and take the point you end up with at the end, and that's the result. Okay. Note, this only works locally because, if I'm say going from a point on the trajectory here to a point on here, maybe 2 steps away or something, I can't get from this left point to the right point by parameterizing in y because it's not an injective function. My parameterization won't work out. But for the last point on the trajectory, you can fill in that little space here with reparameterization in y, and you should be all right, so long as the trajectory isn't really crazy right there. So if you're using small enough step sizes to begin with, then you shouldn't have any problem. This can be, you would calculate calculate your dynamics in terms of u, with u reduced out of the equation, a system of equations. And once you've done that, you can just write a solver that you use for all the trajectories. So once you've done this method for one point on the return map, you can then run it right here again, and then you'll run the usual trajectory. And then when it comes back, it'll jump to here, say, and then you can just use the reparameterization in terms of u and stop exactly here, and you're good. So this only has to be done once per system, and then you can just save your reparameterized system and use it again for other points. So it's quite convenient. And you should often get a point, a port of your system from one parameterization in terms of the system parameters to the other setup where you've reparameterized in terms of u instead of t. So it may be the case that even for different sets of parameters, you only need one reparameterization programmed into the computer. Otherwise, you can do something algebraic, doesn't matter. But that concludes all the material in chapters 1, 2, and 3 of Chaos Book. Again, there are some more terminological components to these chapters, but all the essential stuff has already been covered, so hopefully I can get through chapters 4 and 5, maybe 6 next time. But yeah, join the Discord and let me know if you have any questions. There's plenty of people on there all the time that will answer any question you have. Thank you for watching, and I guess I'll see you next time.